recording all of this. Whoops, sorry. Okay, so we've got an object. We know that there's a force of static friction, an applied force, force of gravity, normal force. We have its coefficient of static friction, we have its mass, and what we're asked for is how much force is going to be necessary to get it to overcome static friction. Well, what we know to be true is the point at which this thing is going to start to move is when the force applied, the moment that this is equal to the force of static friction max, yes? Equal and opposite. That's when it moves. Okay. So what we're really looking for is that the magnitude of the force of static friction max. The magnitude of force that's necessary to break it free. Okay, so let's do some sum of forces stuff, not just because we can, but because it's useful to us. Okay, so if we look at sum of forces on the y, which is not the axis on which the motion is happening, why would we do it? Why would we do this? Because we have to solve for normal force. We're not given normal force. So we know that this thing is not rising into the air or sinking into the earth, therefore that's equal to 0. And it's also equal, of course, to f of g plus f of n. Okay. As long as this thing is not rising or sinking, that means that f of g, or negative f of g, is equal to f of n. Make that n smaller, please, Moser. There we go. Okay, so we've established now what the normal force is. So that's the negative of mass gravity is equal to the normal force. Good. Good, that's useful. Let's sort of set this aside.
What's the force say that's got the arrow pointing at force applied?
This one?
No, number one.
Oh, force of static friction, F sub S.
Or wait, no, over. Like the
Oh,
decorations.
here.
Yeah.
Okay, the decorations. That's what that said. It moves when the force applied is equal and opposite to the force of static friction max. So that point at which it's going to break free, and again, if you've ever gone out and pushed on something or pulled on something, you know, like you apply force, you apply force, you apply force, and eventually maybe you break it free. That's the point at which it starts to move. Okay, so we have this nailed down. We have this. What we're really looking for is this. So let's take this equation and rearrange it to solve for that. Couldn't be much easier. Mu s times Fn is equal to the force of static friction max. Okay. We're given this. We now know this. So we have mu s times the negative of mg equals the force of static friction max. These are pretty simple. For the most part, what you're looking at in these problems is an equation that involves the coefficient of friction and figuring out normal force gravity. So I'll let you plug some numbers in. Okay, so this is our raw number. We sig fig it out. We get that as the force that has to be overcome. Okay. The trickier ones are the ones where it's not a flat surface. So we're going to do one of those together. Number 4 is like that. It's based off of number 3. So let's copy some facts over. Zoom recording. Okay, so we have this wagon on Baldwin Street, and child and wagon are sliding downhill at a constant velocity. What's the coefficient of kinetic friction between the tires of the wagon and the pavement? Anybody have any issues with this problem? Aside from imminent danger to children kind of problems with this, anybody have any problems with the text of the problem? Anybody take issue with anything that doesn't appear that you're given? You're not given any force of kinetic friction. You're not given any mass. You're not given much. What the heck? This is the beauty of a lot of things. So, you'll see. We'll be doing several problems like this. You'll like them. You know, maybe. Okay, so first of all, the normal force is only going to be equal and opposite. Here is F of Gy. And let's do F of Gx. So we've got gravity broken up into two distinct pieces. That's our 38-degree angle. You can do the geometric proof yourself if you feel the need. So what we're looking for is the coefficient of kinetic friction. Oh boy. Well, what things do we know? What things do we know? So first of all, let's do some sum of forces work. Sum of forces on the y is equal to 0. Wagon and child are not rising up into the air, nor are they sinking down through the pavement. And what are all of our sum of forces? What are all of our forces on the y? F of Gy and F sub n for normal force. And so you know, we know then that negative F of Gy is equal to the normal force. Can we break that expression for F of Gy down anymore? Go ahead. Negative of F of G times what? Cosine?
You got that 38 degrees from number 3.
Yeah, you got the 38 degrees from number 3.
Oh, okay.
Okay. Now, can you break that down any further? Because, Frank, mg, because we don't have the tools here to find F of G, because we're not given mass. So what does that tell you you're going to have to do at some point in this process? Factor out the mass. You're going to have to get rid of the mass. Okay, so negative mg cosine theta equals F sub n. Okay, good. We have a nice little expression that we can use. Because, of course, mu k, the thing we're looking for, is equal to, okay, I'm going to screw this up again, F sub n is on the bottom. See, if only I had a note card. Okay, is equal to that. Well, now we've got something we can put in for that. Let's do a sum of forces on the x. What is the sum of forces on the x? It's equal to a couple different things, right? It's equal to mass times acceleration, yes. Okay, because we've tilted the x-axis like we always do. What's the acceleration? 0. So sum of forces on the x is also 0. Well, that's handy. And what forces do we have on the x-axis? We have Fs. We have F of Gx, and if it helps you, transpose that. Okay. All right. Well, what this is telling us then is that F sub s is equal to the negative of F of Gx. And I think based on what we did in the last problem, you can see where this is going. Recording. So now we have an expression for Fk, and we have an expression for Fn, so now we're ready to proceed. So mu k is equal to the negative of mass gravity sine theta over the negative of mass gravity cosine theta. See where this is going? Now I always have to sort of rewalk my trig functions to remember, or trig identities. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, hypotenuse over adjacent, opposite over adjacent, TOA, yeah. So mu k is equal to the tangent of theta. Okay, so we get a mu k of 0.78128, etc., etc., etc. Now, philosophically, I have some issues with that. It's beautiful algebra. It's pretty. I believe the math, but I have philosophical issues with it in the real world. But whatever. Who am I to judge? So that's how to do one where there's no mass. What I'll have you do is get started on the odds, and I'll give you the rest of this period to work on the odds, and probably a little bit of next period. So I want you all to get through a few of those, and then we'll start talking about the 4D stuff. Okay, so more 4C work on your own. If you do not have school, if there is a snow day on Thursday 2/5, you are to go through sample problem 4D, page 146, and get started on practice 4D, numbers 1, 3, and 4 on your own. We'll start on the worksheet together. Okay, that's it.